Okay. Hello, everyone. Welcome to our fluid seminar today. So today we have the pleasure of hosting Cecile Clavaud from IST Austria. Easter, no. So Cecile got her PhD from Marseille, 2015, 2018, and then she did a 2-year postdoc in OSPCI, and now she's doing her postdoctoral fellowship in Austria. So she's going to talk about shear thickening in dense suspensions for us today. So without further ado.
Thank you. Do I present in English or in French? Does anyone have a preference? Okay, yeah, I can do it in English. I can do English. Let's do English. Thank you. Thank you for inviting me, and I'm going to present today what I did during my PhD in Marseille, which was studying shear thickening in dense suspensions experimentally. So first of all, what is shear thickening? It's the brutal increase in viscosity of a fluid, of a complex fluid, at high shear rates. And the most famous example is cornstarch in water, which allows you to walk or really run on water. And the framework of what I did, of my work, was Okay, so why do we have shear thickening? There was a number of explanations. The most common when I started my PhD was that there was some, it was the lubrification force between the grains that prevented them from getting into contact and formed hydroclusters. And then there was this new model, which we call now the frictional transition model. And the idea of this new model was that the grains in a shear thickening suspension were frictional grains with a short range repulsion. So what this does, if you do dimensional analysis again, is you have another force scale. So you have the hydrodynamic force scale and the repulsive force scale. And so you do dimensional analysis again, and you have again that the suspension viscosity is the fluid's viscosity times the function of the packing fraction, and then the ratio between hydrodynamic forces and repulsive forces. And so now you have a viscosity that depends on the shear rate, because the hydrodynamic forces depends on the shear rate. But how does that give us shear thickening? Well, the important thing is to know, the important thing to know is that the critical packing fraction depends on the microscopic friction coefficient between the grains, mu p. And so if the grains are frictional, the suspension will live in this frictional branch, and it will diverge at a critical packing fraction, which is around 58%. And if the grains are completely frictionless, if their microscopic friction coefficient mu p is 0, the suspension will live in this frictionless branch, which diverges at a higher critical packing fraction. And so for a suspension that follows the frictional transition model, what happens is that if the hydrodynamic forces here are lower than the repulsive force, then the grains will not be able to get into solid contact. They will sort of like slide around each other, and the suspension will live on this frictionless branch. But if we drive the system harder and the hydrodynamic forces become larger than the repulsive force, then the grains will be forced into solid contact, and they will dissipate energy through friction. And the suspension will live on this frictional branch. And so at a given packing fraction, because it doesn't change whether the hydrodynamic forces are high or low, you will have shear thickening, because the suspension will go from living on this frictionless branch and jump to this frictional branch. So the frictional transition model nicely explains shear thickening, and the goal of my PhD was to see whether or not this was the actual explanation for the microscopic origin of shear thickening. So to test for this model, you have to access the frictional properties of the suspension. And how to do this? We cannot do standard rheology, which is imposed volume, because this gives access to the shear stress and the viscosity, but it doesn't give access to the frictional properties of the suspension. So we have to turn to pressure imposed rheology. And so there was a need to develop new ways to measure suspension's frictional behavior, and I used rotating drums, which was sorry, I've lost my word, which came from granular physics, granular material physics, and then we developed the Darcytron, which is a new type of rheometer that I will tell you about in the end. Just a quick word on working with pressure. I explained the frictional transition with the repulsive force, and now we're going to work with pressure. It's exactly the same. You just do a repulsive pressure with the repulsive force by scaling it, by dividing it by the square diameter of the grains. And then it's exactly the same. So, first batch of experiments were rotating drums experiments. What's a rotating drum, for those of you who don't know? It's like a very flat cylinder in which you put the suspension. We used non-buoyant suspensions, so we have a sediment at the bottom of the drum, and then we rotate it at very low rotation speeds, so we stay in the quasi-static regime and we have a steady avalanche. And in this regime we have a small thin layer of grains that flow on the slope. In this layer of grains we can write the shear stress and the particle pressure. And by definition, the macroscopic friction coefficient of the suspension is simply, by definition, the ratio of these two quantities, and so it's simply the tangent of the angle, of the pi slope angle. And one thing that's known, and that is nice for us, is that the macroscopic friction coefficient of the suspension is a direct image of the microscopic friction coefficient between the grains, and so by looking at the pi angle, we can actually probe the frictional state of the grains in the suspension. So we have the pi angle theta that gives us access to the macroscopic friction coefficient of the suspension, and then because it's a surface flow, we have access to this frictional property at low particle pressure. So the first thing I did was to compare a classical suspension of glass beads, large glass beads in oil, with a shear thickening suspension of potato starch in water. And this classical suspension is nicely Newtonian. Its viscosity doesn't change with the shear rate, and the potato starch in water is shear thickening. So that gives us, we have a benchmark case for something that should behave like hard spheres in the Newtonian fluid, and here we have our shear thickening suspension. So if we measure the steady avalanche angle in a classical suspension, we obtain about 25 degrees, which means that the friction coefficient of the suspension is about 0.5, which is a normal standard value for frictional grains. And if we do the same with a shear thickening suspension, we see that it flows at a very much lower angle of about 8.5 degrees, which means that the friction coefficient of the suspension is about 0.15, which is very close to a completely frictionless, an assembly, a suspension of completely frictionless grains. And so with this, we see that shear thickening suspensions have a nearly zero frictional coefficient between the grains at low particle pressure. But we wanted to test another way, another image than just the pi slope angle. And so we went to probing the frictional behavior of the suspension with compaction and dilatancy. So I'm going to show you a little movie to explain what I mean with this. So it's two bottles. Is it playing? I didn't hit play. It's two bottles that contain sand and water, and they're being shaken, and then they will be left to settle. And on the left-hand side, once the sand has settled, the bottle is going to be compacted by tapping on it, and then both bottles are going to be put at an angle. And if you watch closely, you can see the difference between the transient avalanche in the left-hand side, where the sand has been compacted, and the left-hand side where the sand has been compacted, and the right-hand side where it hasn't. You see that on the right-hand side it flows suddenly and relaxes at a low angle, and on the left-hand side it just started flowing, and it flows more slowly, and it relaxes at a higher relaxing angle. So basically, that's what we expect for frictional grains. When you resuspend all the grains and you let them settle, frictional grains will settle at the random loose packing fraction, and then by giving it energy, so by tapping on the bottle, you can compact the sediment. And you can compact it above the critical packing fraction, so you can put it in a state where it cannot flow. And then if you impose an angle that is higher than the steady state angle, the steady avalanche angle, which is here, so you impose a higher angle, because the suspension is in a compacted state above its critical packing fraction, it must first dilate, and it must first get back down to the critical packing fraction before I should have brought water before it can flow. So you have a delay time, and then you have a slow avalanche, and it relaxes nicely at the steady avalanche angle. But if you start with a loose state, you give it a lot of energy by inclining the bottle, and so the avalanche starts right away, and then it relaxes at a lower angle. And that's completely different for non-frictional grains, because non-frictional grains will settle directly at the critical packing fraction. So they don't need to dilate to flow, but they are at the critical packing fraction, so the avalanche is not very fast. There's no delay time, and they relax at the steady avalanche angle. So we tested this with our two suspensions. We did the same experimental protocol as the bottle, but with the rotating drum. So we just resuspend everything, let the sediment, compact the sediment by tapping on the rotating drum, and then impose an angle and watch the transient avalanche. And what we can see is that the classical suspension can indeed be compacted above its critical packing fraction. And we see that the more compact it is, the longer the delay time is, and all the compact avalanches relax to this steady avalanche angle. And the shear thickening suspension cannot be compacted, and all of the transient avalanches are more or less the same. There's no waiting time, and they all relax to the steady avalanche angle. There's a slight difference between the different states, and that's, we think, because potato starch grains are not perfect spheres, they're ovoids, and so even if we don't compact the sediment, we probably change a little bit its structure. But so as we can see here, we have, for the shear thickening suspension, no compaction, no dilatancy, which means again that it has a frictionless state at low particle pressure. So that's what we've seen so far with the rotating drums. With our shear thickening suspension, we've shown that there was a low steady avalanche angle, no compaction and no dilatancy, and so this frictionless behavior at low particle pressure. But where does this behavior come from? At the beginning, I told you about the frictional transition, and so this would come from the existence of a repulsive force between the grains, but we don't know what this repulsive force is for cornstarch grains, or, sorry, potato starch grains. We looked through the literature. There were some articles, mainly in food journals, that talked about the existence of short polymer hairs on the surface. So it could be steric repulsion, but this was complicated for us because there was not a lot of literature and not a lot of ways to understand and or control this repulsive force. So we turned to a model system of silica beads in water plus ions. The reason being that silica beads, when immersed in water, acquire a negative surface charge, so there would be an electrostatic repulsive force between the grains that we can control by adding ions. So the range of the repulsive force here is the Debye length, and the more ions we add in the medium, the smaller the range is. So we can effectively cancel out this repulsive force. So we did exactly the same things, measured the rotating, the steady avalanche angle, compaction and dilatancy with this system, both in pure water and in saline water. So what we see is that in pure water we have a very, very small avalanche angle. We measured 6 degrees, which is very close to the theoretical value of 5.76 degrees of perfectly monodisperse frictional spheres. So we're very happy about that. And as you can see, there is also no compaction and no dilatancy. And so with this system, we showed that the presence of a frictional force between the grains in the suspension leads to the existence of a frictionless state at low particle pressure. But having seen that, now we have the two extremes, so we have the frictional state and the frictionless state. Now we want to see the frictional transition. So we varied the salinity of the water, and we see that we gradually go from a frictionless state at very low salt concentrations, and we increase the salt concentration, and we transition to a frictional state. Now the question is, how does this compare to theory? Because theory doesn't talk about salt concentrations, it talks about repulsive force and repulsive pressure. So to compare this with theory, what we need to do is to say that the transition should happen when the equilibrium distance between two grains, that is set by the balance of the particle pressure and the repulsive pressure, is equal to 2 times here the typical length of the roughness on the surface of the particles. And so if we write the force balance or the pressure balance between the particle pressure and the repulsive pressure, it gives us this very nasty equilibrium distance. And the important thing is that when this equilibrium distance is equal to 2 times the roughness, this gives roughness divided by the range of the force is equal to about 2. So if we replot this plot, instead of plotting it with respect to the salt concentration, we plot it with respect to this roughness divided by the range of the repulsive force. We see that it holds. So we have a frictional transition that happens when predicted by the theory. But now, I still haven't talked about shear thickening, and so I said at the very beginning of this thing that this suspension was a model suspension, a model shear thickening suspension, and I have yet to prove it to you. So does this frictionless behavior at low particle pressure actually lead to a shear thickening behavior? It does, or I would not be talking about it. So we linked this behavior to the rheology, and as you can see, when there exists a frictionless behavior at low particle pressure, we have typical shear thickening rheology. So the percents here are the packing fraction in the suspension, and when the repulsive force is screened by the ions and the frictionless state disappears, so does the shear thickening rheology, and so we just kill this shear thickening behavior. So what we've seen so far with the rotating drums is that shear thickening suspensions at low particle pressure have a frictionless behavior, and with this model suspension with a controlled repulsive force, we saw the frictional transition and the fact that the presence of the repulsive force leads to a frictionless state at low particle pressure, which itself leads to shear thickening. But with the rotating drums, the pressure on the flowing layer of grains is imposed because it's the weight without the contribution of the water of the flowing layer, but it's not controlled. So we do not impose the pressure, it's just imposed by the system. So we wanted to be able to impose, to control this pressure, and we developed a new rheometer which we called Darcytron. So there was already at least one rheometer that we knew of that allowed for pressure-imposed rheology that had been developed in the lab that I was doing my PhD in, where the pressure was imposed by a rigid mobile grid. So basically the idea is that it's an annulus, and the pressure is imposed by a grid that pushes on the grains and then can rotate, and then this is all connected to a rheometer head, and you measure the torque and you do standard rheology with this. But the problem with this, so this rheometer actually was used to nicely measure the I lost my word again. Constitutive laws of dense suspensions. So that was very nice, but for us it wouldn't work because shear thickening suspensions have typically very small grains, and so this here in the sides would have to be very well controlled so that the particles couldn't escape this way, and so it would have to be tuned to at least 50 microns, which is too complicated. So we decided to do something else, and we decided to use a fixed grid and impose the pressure through a Darcy flow. So the idea is that we have the cell here, and at the bottom of the cell we have a tube with which we can impose a height difference between here the level of the fluid in the cell and the level of the fluid at the end of the tube. So by playing with this height difference, we can impose a Darcy flow through the sediment. Again, this is with non-buoyant suspensions. And then with this tool connected to a rheometer head, we can just rotate the tool again, measure the torque. Ok, alors par contre, je sais pas si je sais parler bien dans un micro comme ça. We'll see. So as you can see, it doesn't saturate here, and that's just because I had like a limited space for the height difference, and this is 1 meter, and I couldn't go higher. So I would have loved to, but it just there was no space and no tubing left. Okay, so to sum up this whole presentation, I put on a master curve both the rotating drum and the Darcy-Tron results simply by using here for the rotating drums the tangent of the angle, and here is the ratio that I talked to you about at the very beginning of this presentation between the applied particle pressure and the repulsive pressure, and as you can see, it holds very well. So the macroscopic friction coefficient of this silica beads in water suspension, which is shear thickening, increases with the applied particle pressure divided by the repulsive pressure, and it goes from a completely frictionless state up to a frictional state. So that was one of the first experimental proofs of how shear thickening works in dense suspensions. The other one was from another group that did their publication at the same time as us, and they looked at the grain level with 1 grain and AFM, and it was all very, very nice also. And this is basically the end of my talk. I just have like 2 slides to say, oh, sorry, this is the end of my talk. This is the take-home message. So basically, non-Brownian dense suspensions in a viscous regime behave like this. If there is a repulsive force between the grains, then there is a frictionless state at low particle pressure, which leads to shear thickening. And if there is no repulsive force between the grains, then the behavior is always frictional, and there is no shear thickening. And also, we need to develop new rheological tools to go beyond just normal standard rheology. So now this is the end of my talk, and I just have 2 slides to tell you what I did after that. So the first postdoc I did at ESPCI, I studied fluctuation dynamics of ultra-thin supported liquid films. So basically I looked at oil films that I thinned with a laser, and then I looked at how the laser was deflected by the surface to look at its surface fluctuation, and we showed that the fluctuation dynamics were modified by van der Waals effects. That was nice. And now I'm in Austria, near Vienna, and I'm working on a project that I started in the group of Scott Wade-Jacatus, and we are looking at active mixing with Quincke rollers, which are non-conductive particles that you put in a slightly conductive liquid, and when an electric field is applied through the liquid, these particles start rotating, and so if you sediment them on the surface, they will start rolling. So we're looking at that for mixing. And that's it. Thank you. Ooh. So usually practical applications are more in the reverse state, where people want to have a very nicely flowing suspension, and so they want to suppress the frictional regime. One of these applications is, for example, the concrete industry. People have been developing superplastifiers, if I'm not mistaken. They add into the concrete mix. And so if I understand this correctly, they sort of get on the concrete particles and they act as a repulsive force. And so they help this way you can put more particles in the suspension and it will stay flowy longer. That, yeah, so we had a collaboration, we had a start of a collaboration with people from the concrete industry, with people who did superplastifiers, but it was just like too many things, so I didn't have time to go this way. But yes, I think it's still ongoing, and it's like in the background they're still looking at this, trying to. I think their goal was to understand how did the superplastifiers worked exactly, what happened. But yeah, we had I should probably have put an image up there. There's like nice images of these new flowy concretes where you can make very, what's the word in English? No, you can make very intricate structures that are usually not possible with normal concrete because you cannot put enough particles. Yes. Yeah, so potato starch is actually a little bit more dispersed than the silica particles, and basically the more you go away from this very ideal case of completely spherical particles or monodisperse, the less it works because the theory is all based on this ideal case. So the thing is the mechanism is still the same, but it's more difficult to measure because other things will get in the way. So you'll have effects of polydispersity, effects of sizes, effects of non-sphericity that will get in the way. Thank you.